Now next topic, scalar and vector relation between angular velocity and linear velocity. Now see here, suppose as shown in the figure, a rigid body is rotating with respect to z-axis as shown in the figure, okay, and here in time interval delta t, our reference particle of the body moves on the circular path from P to P dash. So we can say its angular displacement in time interval delta t, that is delta theta. But now here we want a linear speed also. So we have to think about linear displacement. So when it is moved from P to P dash, then it is executing circular motion. So we can say the linear displacement, that is arc PP dash. That is arc PP dash. So here by definition we can say average linear speed, that is linear displacement arc PP dash upon time interval, right? So arc, that is angle into radius. So we can write arc PP dash, that is r delta theta upon delta t. So average linear speed, that is equal to r into delta theta by delta t, that is average angular speed. Or simply we can write by taking instantaneous linear speed, v, that is by taking limit delta t tends to 0, v that is equal to r d theta by dt. So v that is equal to r omega. This one is the scalar relationship between angular velocity and linear velocity. Now here we want the vector relationship. So vector relationship means on right hand side say r, that is the position. So we can take it as a position vector r. Omega, that we can take angular velocity, both are vector quantity. And result we want linear velocity, that is also a vector quantity. So on right hand side there is a product of two vectors, and result on left hand side we want vector quantity. So very simple thing, we have to take vector product on right hand side. Now here if we think about the vector product on right hand side, then two possibilities are there. You can write vector v equal to vector r cross vector omega, or you can write v equal to vector omega cross vector r. But we know this thing, r cross omega and omega cross r. These two are equal in magnitude but not in direction. Directions are opposite. It implies that both the relationship are not true. So which one is true one? Let's think about v equal to r cross omega. Now we already discussed here in this particular case, your omega, that is in upward direction. This is your rotational axis. Your body is rotating like this. So thumb is in upward direction. So now think like this. This one is in upward direction. Itself is your omega. Okay? Now this one is position vector r. Now we want r cross omega. Okay? So we have to place again here the right hand screw as we discussed for the direction of vector product of two vectors. We have to place this right handed screw perpendicular to both omega and r. Now we want r cross omega. So we have to rotate this right handed screw from r to omega. R to omega. So rotate this one like this. Okay. So now if you want to rotate this one in anti-clockwise direction, then encircle your fingers like this. Then thumb shows this thing. This will transverse in outward direction. So if this one transverse in outward direction, so if you place this vector here, then velocity that will be in tangential direction outward. But see, in our case, velocity that is inside here, see tangential. It implies that if you take r cross omega, you are getting outward direction. Now you can easily understand, if you take omega cross r like this, then if you rotate right-handed screw in this manner, thumb pointing inward. So that particular relation represent the correct direction. Means this relation is not valid one, but this one is the correct relation. So we can say now scalar relation between linear speed and angular speed, that is v equal to r omega, and vector relation between linear velocity and angular velocity, that is vector v, that is equal to vector omega cross vector r, right? Because we discussed this thing, this one is not representing the proper direction. So correct relation, that is omega cross r. Clear to all of you?